Have you ever heard that we're on the brink of a new gold rush, but this time, it's in space? That asteroids are packed with trillions of dollars worth of precious metals, just waiting for us to go and grab them. It's a captivating idea, often featured in science fiction and hyped up in news headlines. We imagine a future where humanity becomes a multiplanetary species, fueled by the unimaginable wealth of the cosmos. Asteroids like 16 Psyche are said to contain more iron, nickel, and gold than all the reserves on Earth combined. The numbers are astronomical, literally. But what if I told you that this grand vision, this planetary gold rush, is more science fiction than science fact? Today, we're going to dive deep into the science and engineering to debunk this popular myth and uncover the harsh realities of space mining. Let's start with the most fundamental challenge, just getting there. Space is vast, and the distances are mind-boggling. When we talk about mining asteroids, we're not talking about a quick trip to the moon. The asteroid belt, where most of these treasure troves are located, is between Mars and Jupiter. To get a probe there takes years. The Lucy mission, for example, will take 12 years to visit 8 different asteroids, and that's just a one-way trip for a relatively small, unmanned probe. Now, imagine sending heavy mining equipment, processing facilities, and potentially human crews. The energy required to launch that much mass out of Earth's gravity well is colossal. Every kilogram you send into space costs thousands of dollars. We're talking about launching entire factories. The fuel requirements for the journey there, for maneuvering in space, and for the return trip would be staggering. A mission to bring back even a small amount of material would require an initial investment of billions, maybe even tens of billions of dollars. The price tag alone makes the whole enterprise seem economically questionable from the get-go. Okay, let's say we've solved the energy and cost problem. We've magically developed super-efficient propulsion, and our rocket is on its way. What happens when we arrive at our target asteroid? This isn't like landing on a nice, solid planet. Most asteroids are not solid, monolithic rocks. They are what scientists call rubble piles, loose collections of gravel, dust, and boulders, held together by their own weak gravity. Imagine trying to land a heavy piece of machinery on a floating pile of sand. The moment you try to anchor yourself or start digging, you risk sending debris flying everywhere, or even completely destabilizing the entire asteroid. It could break apart, sending your very expensive equipment tumbling into the void. Mining in microgravity is a nightmare. On Earth, gravity helps us with everything. It keeps our tools on the ground. It helps separate materials, and it provides a stable platform to work from. In space, none of that applies. A simple shovel becomes a projectile launcher. Dust and small particles don't settle. They float around, creating a hazardous cloud that can clog machinery, damage electronics, and pose a threat to any solar panels. So, how would you even mine this stuff? One idea is to capture the entire asteroid in a giant bag. Sounds simple, right? But again, you're dealing with a spinning, irregular-shaped object. Capturing it without breaking it apart or sending it into an uncontrolled tumble is an immense engineering challenge we haven't come close to solving. Another idea is to use lasers or focused sunlight to vaporize the rock and collect the valuable elements from the resulting gas. This is called In-Situ resource utilization, or ISRU. It sounds very futuristic, but it requires an enormous amount of power, and the technology is still in its infancy. We'd have to build and deploy massive solar arrays or a compact nuclear reactor, all of which adds more weight and complexity to the mission. We'd also need a mobile factory that can process the raw ore and separate the valuable metals from the worthless rock, all operating autonomously in a vacuum, with extreme temperature swings. We are decades, if not centuries, away from having this kind of robust, reliable technology. Now, let's talk about control. You're trying to operate this complex, delicate mining operation millions of kilometers away from home. Communication isn't instantaneous. Depending on where the asteroid is in its orbit, the time delay for a signal to travel from Earth to the asteroid and back can be anywhere from several minutes to almost an hour. This makes real-time control impossible. You can't just joystick a robot arm like in a video game. If you see a problem, by the time your command to stop reaches the mining bot, it might be 40 minutes too late. The entire operation would have to be almost completely autonomous. The robots would need to be able to analyze their environment, make complex decisions, and troubleshoot problems on their own. We're talking about a level of artificial intelligence that is far beyond what we currently have. Our most advanced rovers on Mars still require a lot of guidance from human controllers on Earth, and they move very, very slowly. A fully autonomous mining operation is a whole other level of complexity. Let's assume, against all odds, we've done it. We've launched our mission, successfully mined the asteroid without it falling apart, and processed the ore in space. We now have a few tons of pure gold or platinum. What next? We have to bring it back to Earth. This means another long, expensive journey, culminating in a fiery re-entry through the atmosphere. You have to design a heat shield and landing system capable of bringing down tons of dense metal safely. Any miscalculation and your multi-billion-dollar payload burns up or crashes, becoming worthless. But here's the real kicker, the ultimate irony of the planetary gold rush. Let's say you succeed. You land your cargo of, say, 100 tons of gold. What do you think happens to the price of gold on Earth? The global market would be instantly flooded. The price would plummet. Gold and platinum are valuable precisely because they are rare. By introducing a massive new supply, you would destroy the very market you were trying to capitalize on. Your trillion-dollar asteroid would suddenly be worth a fraction of that, potentially not even enough to cover the astronomical cost of your mission. You'd go bankrupt by being too successful. So, is asteroid mining a complete fantasy? Not entirely. The true value of asteroids might not be in bringing precious metals back to Earth. The real gold in the asteroid belt is much more common. Water. Water, when broken down into hydrogen and oxygen, is rocket fuel. Asteroids and comets are full of water ice. If we can learn to extract it in space, we can create orbital gas stations. This would be a game changer. Ships traveling to Mars or the outer solar system wouldn't need to launch with all their fuel from Earth. They could refuel in orbit, making deep space exploration much cheaper and more feasible. Other common materials, like iron and nickel, could be used for in-space construction. Instead of launching everything from Earth, we could 3D print habitats, tools, and even spacecraft components using materials already in space. This is the real, practical vision for asteroid mining. It's not about getting rich quick by flooding Earth with gold. It's about building a sustainable, long-term human presence in space by learning to live off the land, or in this case, off the asteroids. The planetary gold rush is a myth, but the dream of using space resources to further our journey into the cosmos is very real and incredibly exciting. It's just a much slower, more difficult, and ultimately more rewarding endeavor than the headlines would have you believe. Thanks for watching. And if you enjoyed this cosmic reality check, be sure to like and subscribe for more deep dives into science and space. See you next time.